Over the last year, AI labs have rapidly expanded context windows, releasing models that can process over 1 million tokens in a single request. This scaling has created a pervasive misconception that developers no longer need dedicated search systems. The assumption is that you can simply dump an entire enterprise codebase or a massive database export directly into the model's prompt. But tokenization is the physical bridge between human language and model compute. Every token processed requires memory and processing power. When you stuff 100,000 tokens into a prompt, the transformer's attention mechanism must compare every token against every other token before it can generate a single word. The cost per query climbs exponentially, and time to first token latency becomes too slow for user-facing products. Even if you are willing to pay for that massive context, you hit a structural limit. Language models suffer from attention diffusion on long sequences. If the exact fact you need is buried halfway through a massive text block, the model frequently ignores it, favoring information at the very beginning or the very end of the prompt. Then there is the security constraint. Enterprise systems require document-level role-based access control. A massive static prompt has no mechanism to verify if the current user is authorized to read specific paragraphs within that data block. You risk leaking restricted content directly through the generated text. Blindly stuffing an entire corporate database into a single prompt violates ASIC system design principles. It creates a system that is slow, prohibitively expensive, prone to missing facts, and impossible to secure. The architectural solution to these physical constraints is Retrieval Augmented Generation, or RAG. To understand RAG, we have to separate a system's memory into two distinct types. Parametric memory consists of the static, frozen weights inside the language model itself. This is where the model stores its reasoning capabilities and generalized knowledge from its initial training. Non-parametric memory is your external database. This is where your organization's true, verifiable data lives: support tickets, financial reports, and internal documentation. A RAG pipeline acts as a highly controlled bridge between the two. Instead of memorizing the data, the system intercepts a user's query, searches the non-parametric database, pulls only the highly relevant evidence, and feeds those specific chunks into the parametric model for reasoning. This design completely decouples knowledge from reasoning. When a company policy changes, you simply update the external database. The system immediately references the new policy, preventing stale answers without spending millions of dollars to retrain the underlying model. In a production environment, a senior engineer's job is not writing creative prompts. It is architecting this exact data bridge to guarantee the language model only reasons over verifiable, permission-controlled truth. The first phase of building that bridge is defining the retrieval unit. Before you can search a massive corpus, you have to decide exactly how much text the system should pull at one time. If you set the system to retrieve entire 100-page documents, you recreate the context window problem. The model is forced to dig through pages of irrelevant boilerplate to find a single metric, increasing the risk of hallucinations and spiking latency. But if you go the other direction and retrieve isolated single sentences, you strip away the surrounding context. A sentence saying sales dropped 20% is useless without the previous sentence establishing which quarter or product is discussed. Chunking slices source documents into readable segments, giving the retrieval engine discrete targets. To prevent cutting a critical sentence in half, engineers configure a 20% overlap. This safety net ensures the end of one chunk shares context with the beginning of the next. The specific size of these chunks directly dictates the model's performance downstream. The chunk must be large enough to contain a complete thought, but small enough to maintain a high density of relevant facts. If your chunking strategy is flawed, you have permanently bottlenecked the system. A poor chunking strategy feeds noisy, incomplete text to the retriever, breaking the pipeline before the language model even sees the data. Once chunked, the system faces a massive computational hurdle, finding the single most relevant chunk among millions of records in a matter of milliseconds. Modern systems solve this using dense retrieval. This method uses an embedding model to convert text into continuous numerical vectors. It maps the semantic intent of the query into a geometric space. Dense retrieval understands concepts, mapping physician compensation to doctor salary trends.
But it misses rare identifiers, like error code 404B. To fix this, Lexical search perfectly captures exact keyword matches. Running both in parallel creates hybrid search, eliminating the blind spots of each method. Even with hybrid search, mathematically comparing a query against millions of chunks is wasteful if the user only has permission to see 10 of them. Metadata filtering allows the system to hard filter the database by tenant ID, date range, or document type before the vector search even begins. By wrapping a hybrid search engine in strict metadata constraints, you guarantee the system finds exact terminology, understands conceptual phrasing, and completely avoids pulling data outside the user's permission scope. Even after filtering, we still have to rank the remaining vectors. Comparing a user's query vector against every single eligible chunk requires an immense amount of compute. To solve this bottleneck, databases rely on approximate nearest neighbor algorithms, typically powered by a Bi-Encoder. This trades mathematical perfection for extreme scale. Instead of calculating exact distances, it navigates the index to find a highly probable neighborhood of relevant chunks at millisecond speeds. But this creates a precision problem. The Bi-Encoder is incredibly fast because it encodes the query and the documents entirely separately. The top 100 results it returns are broadly relevant, but they are rarely ordered perfectly. To get the best evidence to the very top of the list, you introduce a cross-encoder Reranker. This is a secondary, highly precise sorting mechanism. Unlike the first stage, the cross-encoder processes the user's query and the retrieved document together. It reads them simultaneously, allowing for deep, nuanced contextual matching that the fast Bi-Encoder cannot perform. Because this simultaneous reading is computationally heavy, it is too slow to run across the entire database. It can only be applied to the small shortlist of 100 results that the first stage already narrowed down. This two-stage architecture is the industry standard. You use fast Bi-Encoders to scale across millions of documents for high recall, and you use heavy cross-encoders on the shortlist for high precision. This funnel ensures that only the sharpest, most relevant evidence survives. It protects the language model from processing noisy context, and it keeps the overall system latency well within production limits. Building this architecture is only half the job. In a professional system design environment, you have to mathematically prove the pipeline actually works before you ever attach a language model to it. Evaluation always requires a strict system decoupling. If you only look at the final generated answer, you cannot tell if a failure was caused by bad data retrieval or by the language model simply ignoring good data. We isolate retrieval using offline metrics. The primary metric is recall at K. It asks, did the correct supporting fact get pulled from millions of database records into the candidate shortlist? If low, the generator never sees the right facts. We evaluate second-stage ranking using mean reciprocal rank, or MRR, and normalized discounted cumulative gain. These metrics prove the Reranker is working. They verify the most relevant evidence is forced to the very top, where the model will actually use it. By tracking these specific offline metrics, an engineering team can isolate problems accurately. It prevents developers from endlessly tweaking prompts or blaming the language model for what is actually a failure in the data pipeline. This diagnostic river is how you solve the ultimate failure mode in generative AI: hallucinated outputs. When a user receives a fluent, confident, but entirely incorrect answer, you consult the scorecard to find the exact point of failure. If your recall at K is low, the required evidence was never retrieved. This immediately isolates the failure to your embeddings or your chunking strategy. The language model is entirely clear to fault. It hallucinated simply because it was starved of ground truth. Conversely, if your metrics show the exact right chunk was retrieved and ranked at the top, but the final answer is still wrong, the retrieval pipeline succeeded. The failure is now strictly isolated to your prompt constraints, a missing fallback policy, or the decoding limits of the model itself. Frontier models are incredibly powerful reasoning engines, but all of that reasoning is completely useless without injected, verifiable evidence. True system design mastery does not lie in relying on infinite context windows or expecting a model's frozen weights to know your business. It relies on architecting a verifiable retrieval pipeline that makes AI reasoning grounded, safe, and economically scalable.